Hello and welcome to video 4 where we're going to talk about memory and caching. Here we can see two images. The first image is random access memory. Now, if you studied computer science at GCSE level, you'll know all about random access memory, and we know that it's volatile memory, which means that when you turn the computer off, all of the information stored on RAM will disappear. Now, what we need to understand is that RAM actually plays a very important part in processing. The CPU's job is to process all of the information. This information comes from the RAM. The RAM gets its information from secondary storage devices. It's important to keep that process in mind for later. The CPU itself is very fast at processing information. Now it's waiting for RAM, which is quite slow, to get this information and transfer it on. The CPU's speed is determined by a clock cycle. A clock cycle is 2 pulses of an oscillator. Now you don't specifically need to know what an oscillator is. All you need to understand is that this is what keeps a steady beat in the processor. Now the more pulses that we have, the faster the processor can execute instructions. Because of the speed mismatch between RAM and the speed of it, and the speed of the CPU, we call this the von Neumann bottleneck. Now this can be massively detrimental to our system because as the data is being executed really quickly by the CPU, the rate at which the RAM can get the information to us in the CPU is very slow. So this causes idling of the processor. So now let's have a look at how we can start to combat the von Neumann bottleneck. And to do that, we use cache memory. So now we say cache memory is the answer to all of our problems. However, it's only one way in which we can combat the von Neumann bottleneck. So cache memory acts as the middleman between our CPU and our RAM. And our little reminders again of our speeds. RAM is typically known as the slowest. Cache is faster and CPU is still the fastest. Cache memory is usually small sized. This relates to the price of cache memory. It is very expensive. It's also volatile computer memory. It has very high speed data access, meaning we can transfer the data very quickly. And it also stores frequently used computer programs, applications and data. Now we've talked about cache as a single entity, we can actually take this a little bit further. Here we can see two different diagrams. The first one being single cache, where the CPU connects to cache and connects to main memory. By main memory here, we mean random access memory. The second diagram is leveled cache, where the CPU connects to level 1, which connects to level 2 and level 3 cache, and then finally to main memory. So what interests me is the second diagram. So let's talk about the cache levels. On level 1, we've got extremely fast, relatively small memory. It's usually embedded into the CPU. By keeping the physical distance very short, it means there's less distance to travel between the cache and the CPU, therefore speeding up the process. Level 2 has a higher capacity than level 1. And what we mean by this is that it's got a bigger size. Now, because it's got a higher capacity than level 1, it operates more slowly. And this may be located on the CPU chip still. It's dedicated to a single core or a pair of cores. With level 3 cache, it works to improve the performance of level 1 and level 2 cache combined, and it's shared by all of the cores. So in your exam, it's possible you might get asked about the advantages of the leveled cache system. It's also possible that you will be expected to talk about cache and how that combats the von Neumann bottleneck. Now what we've explained so far is all well and good. If the CPU needs information, it will go into cache and see if it's got it. If it's not inside cache, we have a problem. We have to go back into RAM and see if the information is there. If it's not, we have to go back into our secondary storage devices to see if the information is there. And all of this process takes time. What I've basically explained there is a cache hit or a cache miss. A cache miss is when the processor requests data that is not inside the cache. This is referred to as a cache miss. A cache hit is when the processor requests data and it is found in cache. The more cache misses that we have, the more inefficient our system will be. Now this is very bad. Cache misses slow down the overall speed of the whole system. The goal of any system should be to reduce the amount of cache misses that occur in any system. Now so far, so good. You've listened to me drone on for over 6.5 minutes about cache memory and how great it is for your system. But what I'm going to tell you now is that cache memory, it does improve system performance, but it is not essential. One thing that is essential that we've not talked about so far in memory is ROM. ROM stands for read-only memory. ROM stores the programs required when the system boots up, making it vital to our system. ROM is non-volatile, so it can store this information quite happily, and the power can be turned off and you will still get access to all of the information needed. ROM also stores the bootstrap program, which tests the hardware is functioning correctly. You might have seen this when you start up your computer. It also stores the basic input-output system, or the BIOS. This stores system configuration information crucial to loading up your operating system. It also includes the boot order of your storage devices in BIOS. Now in this video, we've discussed memory and caching. So in your exam, you need to be happy that you can talk about the different types of memory discussed in this video and what caching is, what it does, how it reduces the von Neumann bottleneck, and how each of the different levels apply between RAM and the CPU. So finally, from me, all that's left to do is to thank you for watching this video, and I'll see you again in the next one.